All right, welcome back, everyone. It's my pleasure to introduce our next speaker. Is Joren Gijsbrechts. So try saying that. So Joren is like me from Belgium, and it's one of those other pleasures of academia that we can work with people from all over the world. After Jan Kun, so we now have Joren. Joren also, you'll see a joint member here. Dennis Zhang is also part of this team. And this was kind of our first experiment going really into deep reinforcement learning. So Joren, it's all yours.
Thank you very much. Is the audio working? Yes, now it is. Thank you very much for the introduction. I'm very happy to present this work. We've been working a long time on it. We finally got it through, so it's indeed a joint work with Professor Boete, which was my advisor in Belgium, Professor Jan van Meegem and Professor Dennis Zhang. So without further ado, let me get started. I was very lucky, I think, when I started my PhD, that I was at the right time, at the right place, at the right moment, because of this breakthrough that happened at the time. I know when I presented this 4 years ago, many people didn't know why I was showing this slide. But I think if I show this slide now, why am I showing this? Who knows the game? Go. Game of Go, yes. And what is it linked to these days? AI, yes, the major breakthrough of AlphaGo. So when I started my PhD, this breakthrough actually happened where a deep reinforcement learning algorithm, AlphaGo, beat the world champion, Lee Sedol. There's a great Netflix documentary about this event, and I got very fascinated. So I was working with Procter & Gamble during my PhD, and they asked me to solve a problem, but they didn't tell me how to solve it. So at that time, I was interested in learning about new methodologies, and I thought, well, this game looks really cool. They beat the world champion, so let me see whether I can use this technique. I got approval from my advisor, and also later on we worked together with Jan on this one. So I thought, okay, this looks very promising, but how can it help our community, right? So it all looks very cool and fancy, but can we learn something with that technique? So it appears, of course, like we know, and also what was already talked about in the first session, that many of the problems that we tackle also suffers from, the curse of dimensionality. So exploding state space, but also indeed exploding action space and transitions, etc. On top of that, most of the heuristics that we use are problem dependent. Now, what do I mean with this? Is that many of the heuristics that we develop, so I'm in inventory control, so I will talk a lot about inventory management. And many of these methods assume, for example, linear sourcing costs. And even despite decades of research, many of the problems we haven't solved yet, right? So we're doing a lot of effort, and we are not there yet. I mean, of course, we have great results. But then if you talk to a company, then very often they say we don't have. These assumptions are not valid for our specific case. For example, the cost may be piecewise linear. So when I was working in FMCG, they had a cost for every pallet that they put in a truck, and every time a new truck came, then there was a fixed setup cost because a new truck had to come. So this is, of course, a very different cost function. And then if you use the heuristics that we develop for linear sourcing costs, then those won't work very well. Of course, you may say, let's hire a researcher who will fix the problem. But of course, this also requires a lot of time to come up with good policies. Sourcing costs may be convex or concave, etc. So this is just to say that the heuristics are typically made for one specific setting. And one aspect that I really liked about deep reinforcement learning is that it really looked like this general purpose technology that could tackle a lot of problems without having to rely strongly on these assumptions, right? Because you could train the algorithm in the cloud and solve a different problem with it, or under a different set of assumptions. Okay, so I started and I thought, okay, deep reinforcement learning to the rescue. The paper of Nature came out in 2016, which was around the time that we started with this project. The problem that I was solving at the time for P&G was the following one. They had to supply their warehouse from a plant, and they were looking at using two different transportation modes. So this problem is known as a dual sourcing problem. I mean, it's mathematically equivalent to ordering from two sources. Either using a fast mode, for example, a truck, which has a higher cost but a shorter lead time, or using a slow transportation mode, a train, which has a longer lead time but a lower cost. Right? So the decision is, every period, how much are we going to order with the fast mode and the slow mode to ultimately replenish the warehouse. So a problem that has received quite a lot of attention actually in the literature. So this is the same as offshoring versus onshoring. Okay, so this was a problem I had to tackle. So when I was a PhD student, I was surprised because I was told to try to solve this problem. And I was quite surprised. So I remember being on the plane reading the book of Warren Powell on approximate dynamic programming, because I knew that the traditional methods, they don't scale very well on this problem. Why is that? Because the pipeline inventory vector can get the state space gets very large because of the pipeline vector of units that are in transit. So I was reading up on approximate dynamic programming. And I was very surprised to know that these algorithms like AlphaGo, under the hood, also rely on the same framework of a Markov decision process. So I started and I modeled the problem as a Markov decision process, where the state space is basically all the inventory you have on hand in the warehouse, but also all the inventory that is in transit and that will arrive tomorrow or the day after or in a couple of days. And the latest period, then 7 days, would be the longest lead time that we were looking at. Now, the actions that we then have to take is, okay, what are the order sizes? So how much do we order from the fast supplier and from the slow supplier? And the cost function, well, basically, and this is also what I wanted to stress in the beginning, basically you can choose which cost function you adopt. In the experiments, we will adopt the more conventional academic cost settings of linear sourcing costs, because then we have very good benchmarks, and then we can show, okay, how well does this technique really work? Remember, when we started this, it wasn't really done yet, at least the part with the deep learning in reinforcement learning. But you could add other kind of rewards, and we saw the first presentation today, also with a multi-objective setting, where we can play with the rewards, and then we can learn from that. Okay, so now, which algorithm did I choose at the time? I chose the A3C algorithm, which at that time was kind of the best algorithm available. So I have to go a bit to the left for the picture. So that was kind of the best algorithm available. So I think deep Q learning made a big breakthrough at that time, playing against Atari. But then this method came out just a little bit later, the A3C algorithm. Now, what is this algorithm? There are several parallel learners. Each have a neural network. The input is always the states, right? So the inventory levels and everything that is in transit. The output is on one side sorry, I'm not sure I have a pointer. Oh, I do. Is on one side a policy. So this will be a stochastic policy. I will show it in the next slide. And on the other hand, a critic. So A3C is coming from actor critic algorithm. The critic gives an estimation on what the cost will be, and the actor tells you which actions to take. Now, in the next slide, I will show how these workers interact with each other. But the A3C algorithm at that time was one of the best algorithms, or the best. Now, the neural network that we then used is also a more conventional neural network in a way, because it's a fully connected neural net. The inputs are basically is the state space, so you have your inventory level and everything that is in transit. What is in transit is a combination of what you order from the fast supplier and from the slow supplier. So we have some hidden layers. Now I'm just showing for visualization just one, but we used 4 layers, fully connected. And the output layer is then has a softmax activation function, which basically creates a probability vector of which orders you can place. That's the actor of the model, and the critic gives you an estimation of what the cost will be. Now, it's true that this actor doesn't scale very well if you have very high dimensional action spaces. For the problems that we tested, we could still do this. Okay, so this was the neural network that we used, and it's really like the core of the algorithm. Now, then, how do we define the loss function of this algorithm? Well, we basically simulate a lot of periods, where we go from one state to the other by taking actions and observing costs or rewards. And after we have such a buffer, we use that buffer to define a loss function. It consists of 3 different parts. One is the value loss, which is intuitively the estimation of the critic. So think about you are, for example, in the first state ST. You make an estimation of what the future costs are going to be. Then you observe a lot of costs, and in the end you end up in a final state ST plus n. And also from there you can make an estimation of what the future costs will be. You compare these 2 numbers and you take the mean squared error, and that's basically your value loss. The policy loss, we have a stochastic policy, so you can look at, okay, which actions, using the critic, which actions gave me better results than others, and you increase the probability of the actions that gave you better results than expected. So that's intuitively what the policy loss is doing. In the paper, you can look at the mathematical formula. And the entropy loss encourages you to explore. So it kind of discourages a probability vector where you have a strong support on one action, but you encourage that the algorithm also explores. Okay. Now, I said I would come back to this, how these parallel learners interact with the global network. So they all have an identical network with different weights. What happens is that at the beginning of the cycle, the worker reset to the global network. So all the workers get the same parameters as the global network. The worker then interacts with the environment. So they simulate and they are in different areas of the state space, right? So that's why we have these different learners, because we want to explore in different areas and we want to avoid that we overfit in on one specific area of the state space. Then the worker calculates the value in the policy loss and the entropy loss, which is what I just explained. The gradients are computed, and these gradients are not directly implemented on the worker, but they are implemented on the global network. So basically the global network gets all that information from the parallel learners. So training then implies we keep doing this loop a lot of times. And this is a picture I'm very proud to show, but I mean at that time it really took me a very long time to get this work. But what did we do? Well, we compared the optimality gap of the A3C during training on a very small problem instance where we could still compute the optimal policy. And we saw here that we ended up with a policy within 2% of the optimal one. And the blue curve is basically the optimality gap during training. So you see that it's still exploring, but we always save the best known policy, and that's the one we will ultimately use. Okay? If there's any questions during the presentation, feel free to interrupt me. Okay, now we chose this specific setting because we wanted to compare, this is a very heavily researched topic, we wanted to compare with the best known heuristics at the time. I think the cap-dual index is really one that performs very well from Yang Kun Sun, who just presented before. So she has several really good or very strong papers, and this one is the robustly optimal policy. So if we optimize versus the robust cost rather than the expected cost, this one is actually optimal. But also in the expected cost setting, this one performs very well. What do we see? The A3C doesn't perform better than this policy. So you could say, okay, that's well really a downside. In a way, it is, but on the other hand, if DRL would really outperform all the policies that all the benchmarks that we have, then there would really not be a job for us left, let's say. That being said, the A3C is very general purpose, right? So the cap-dual index policy works very well on this setting. But then if you would apply it on a different cost function, then that policy may be performing very bad. We do outperform, like for example, the single index policy, and are more or less in line with the others. So these were the numerical results that we have, but we have still quite small optimality gaps within 2%. We also tested a different problem, so the lost sales, and this is really where the power of the algorithm then really starts to shine, because the same algorithm which we tuned, we then also applied in the lost sales setting. So no longer can you order from 2 different sources, just from one source, but sales are no longer backlogged, but they're lost. Again, an intractable inventory problem, and here we see that again A3C performs comparable with other policies. Okay. Now we did a huge sensitivity experiment where we tested a lot of settings, did a lot of training to see how does different parameters impact the policy performance. And we saw that many of the results the results are very robust in terms of changing the parameters. For example, in lost sales, we changed the lead time. We compared them against the other policies that we benchmarked against before, and you see that many of the results stay more or less the same. Okay. So this is, of course, one slide, but it did take quite a long time to get all these results. We also compared against approximate dynamic programming, where this time we don't use a neural network, but here we used a linear programming, approximate dynamic programming. A cool thing of this specific method is that for lost sales, we know what the structure of the value function is. It satisfies a certain property which is called L-natural convexity. Because of that, we can use a polynomial expression for the value function, but the parameters of that function we find using linear programming. So we simulate a lot of experiences. We then fit using linear programming these parameters, and then having this approximate value function, we then derive the policy. Now this method, we thought, okay, this is going to be a very strong benchmark, but we also saw it really suffered from, it's very strong dependence on which samples you basically used. So the myopic policy, which is used to sample the policies, is your red line over here. And you see that the blue algorithm actually didn't perform that well. Now the paper didn't end up being published, so maybe that's also one of the reasons. But we tried to have a strong performance benchmark versus what was the state of the art. The third benchmark we did was the multi-echelon setting, and here we saw we used a rather simple setting, but we have 2 echelons and several retailers here. And here we saw comparing against a constant base stock policy, which was also the cost that was policy that was used in our benchmark paper. We do have larger savings, right? So here we save 9 to 12% for 2 settings that were also considered in that paper. So this was a very old paper from Van Rooij, and they also used even some neural networks in that paper. Okay. So lastly, this problem was, of course, very inspired by an industry setting, and we've been testing it quite a lot in stylized settings. I also applied it on data. So this is a product that you see. So in terms of how many pallets per day we sell, so from the consumer goods industry. We tested 2 different ways of training. So this was a corridor from France to Italy, where both road and rail were used with a lead time of 4 and 7 days. We tested it on one SKU which had a high volume. It was a stationary SKU, so there is quite some variability, but still stationary. I will come back to that because I think there's still quite a lot of work to be done in applying these methods in non-stationary settings. The cost functions that we employed is that cost function which I described in the beginning, where we have this piecewise linear cost function. Okay, so what did we do here? Of course, here we don't have the optimal policy. So we came with a technique where we said, okay, what's the expected value of perfect information? So assume you know exactly what the demand would be, then the policy becomes rather trivial. So you can just order always using the cheapest supplier exactly what the demand will be. So we use that to compute, like, okay, if you increase the coefficient of variation of your problem, what's the gap between the optimal policy and the oracle policy, which is better than optimal because you have perfect information. We saw that difference scales linearly. So this is something that happens sometimes in inventory problems. We saw that it also happened in our dual sourcing problem, and then we boldly extrapolated this property to get an estimation on our problem setting where we couldn't compute the optimal cost anymore. What the difference would be between an oracle policy and the optimal policy. Because the oracle policy you can always compute. You can always assume, like, okay, I have perfect information on data. I know what my policy is. So for our problem, we used extrapolated optimality to compare. And what we saw that then on that setting is that we performed approximately 6 to 7% from optimality. So that was on the real data set. Now, to get all these results, we had to do quite a lot of work. The tuning was really intense. I think at one point So definitely in the beginning it was very discouraging without a lot of computational power. So what we did is in the beginning we prototyped a lot to try to see roughly what works well and what doesn't work well. We found that especially the learning rate and the entropy of the A3C algorithm were important tuning parameters. We visualized this with an ellipsoid, so we kind of fitted over the hull of all the runs that we have to kind of see what is the region where the policy performs the best. So you see these are the stars you see are the points on the convex hull of that ellipsoid. To give intuition, like, okay, where should you start if you would start with a new problem? And starting from these parameters, we kind of made a set of hyperparameters that performs well, which we then applied later on in that numerical sensitivity analysis that we did. Because we did do like thousands of training runs. Each of them is millions of simulations, so there's a lot of computation going on. And with this, we try to give intuition which parameters that you can use if you would start with tackling a new problem. Okay, so the conclusion of this paper was rather nuanced. So it seems like DRL is a promising general-purpose technology because it was effective at solving several inventory problems, especially when these problem-dependent heuristics are lacking. Right? So if you don't have a very good benchmark, then this could be really a good algorithm to start. Now, it often remains a black box, so I'm going to come back to that after this because I have some follow-up work as well. And the computational effort is very large, right? So this was the conclusion of our work. Okay, so now this was like at that point one of the first works in inventory management. I think together with the beer game paper, we used deep Q learning. The first papers to really show that it works. Now the question is, okay, what are we going to do now? So I was talking before with colleagues from the Netherlands. So there's quite a lot of people who are also now working with reinforcement learning. But the question is, okay, where do we go from here? Of course, I don't know, but there are some research directions that I think are interesting. One thing we are testing is reward shaping, or we have tested it actually, where we use very good heuristics to steer the learning of the algorithm. And so a lot of the reinforcement or the deep reinforcement learning literature that is appearing now in computer science is for robotics, where it's kind of hard to define a reward function. So you may know what a desirable behavior is, but it's not so obvious what a good reward function is to get to that behavior. If a robot has to pick up something, then how do you create the rewards to reward that behavior? In inventory management, typically we have a very well-defined cost function, but still. So a lot of work has been going into reward shaping. Now, what have we done? We use a potential-based function. So we say, well, let's say we have a very good heuristic, right? So the best-known heuristic that we have on one specific problem. So this one we did for perishable inventory, and we modify the reward function of the MDP. So what we do is, if you see like the visual presentation here, is for state action pairs, we will say, well, certain state action pair, we say they are a little bit better than others. And how do we do that? Well, we basically measure the distance between this weird little a here, which would be the action taken by a very good benchmark, with the action that the algorithm is actually proposing. So if you are very close to the action of the expert, let's say, so the expert heuristic, then that is good. If you are far from that, then we assume that is bad. And this way you are training and you're kind of staying in the same line as what the expert heuristic is doing. And this we kind of inject into the reward that the algorithm is observing. So there are more details in the paper below. But what we saw is that, and here we use deep Q learning, is that if you use unshaped DQN, this is the blue line, so it trains rather well, you could say. But if you then use these shaped methods where we use the base stock policy and a base stock policy where we included the expected waste, so this is perishable inventory management, then we saw that the algorithm trains smoother, first of all, so there's less variability on the training, which makes intuitively sense because you stay closer to that expert heuristic. But it also trains deeper, right? So it gets closer to the optimal policy, which is promising. Of course, it goes a little bit against what I said, like DRL is very interesting if you don't have benchmark heuristics. But still, a lot of companies will have a heuristic that they're currently using, so that would be the most obvious one to use. So you could make the training maybe on initial tries using that benchmark of a company. Yes, Jan?
How much better is your learning policy relative to your expert policy?
Yes.
Can you repeat the question?
Yes. So the question is, how much better is the Q-learning algorithm now relative to your expert heuristic? So on this work, we also had rather small optimality gaps. So here we were testing it on optimality gaps where we are below, well, around 1%, let's say. So that's that's the starting point, let's say. That's where the expert heuristic is, and we managed to dive under it for several settings. So, and we were then between, let's say, 0.5% and 1%. So now I think there's of course also tuning that you can do to in the beginning say, like, let's learn towards that expert heuristic, and then let's try to relax a little bit and start more exploring from there. Yes. So this is one thing we did. Now, there's still some limitations in practice. I think one of the things I like the most about the original paper which I presented is that there was quite some interest from the industry. So I got contacted quite a lot by firms that said, like, we want to do something similar, or we're trying to do it. And I just want to give like 3 things and share it with you, which I think companies really need at the moment. One thing is, well, deep learning really remains a black box. And I think, so you train something, then you push states through a neural network, you get the actions, but all the companies I've been working with, they always start looking at the output and they don't understand what's coming out. So I've been in a lot of meetings where I just get, basically they show me the visualization of the policy and then they don't know how to basically go from there. So I think there's a lot of needs to circumvent this. Otherwise, it will be very hard to apply the policies in practice. I'm not sure. I mean, this is also not something that is only related to deep learning, but for some reason, a lot of firms, when they use a deep learning algorithm, then they start to heavily focus on trying to interpret the results. While if you would use, integer programming or whatever, then they don't want to understand the policy structure, but they still believe the algorithm itself. So, but for deep learning, that's really not the case. So I think there's a lot of work to do on this. There's also a lot of work on just in general interpretability. Yes?
Why is that? Why, when they do integer programming or functional optimization, they don't care about the structure, but for deep learning they do? I'm curious.
Yes, I think.
Repeat the question.
Yes. So why do companies care so much about the fact that a deep learning algorithm is a black box versus for other algorithms they wouldn't? I think one of the reasons is that there's a lot of variability on deep learning, right? So you may train 100 times and you will get 100 times different results. Some of them will be very good, but a lot of them will be very bad. This is also something that, and that's why we showed the ellipsoid, where you saw like a lot of the policies were worthless. This is something that's also our task as researchers, to not hide those results, because this is what's happening if a paper says, like, it works really well, and that's one setting where it worked really well, then companies try to apply it in practice, and then if it only works one time out of 50 times, they are very concerned, right? And that level of concern really starts to results in a lot of questions and a lot of follow-up in trying to deep dive understanding what the algorithm is actually doing. Now, there is research in interpretability, so we can actually try to do that. But maybe we should try to use our algorithms smarter. Okay? And I think the paper, where we start with the presentation today also is if you embed heuristics, or a lot about the policy structure, you can also use reinforcement learning in combination with that policy structure to, for example, learn the policy parameters. And then, at least you have the policy structure right. A second one is learning in dynamic environments. So a lot of the in dynamic environments in inventory management, I'm more alluding at, for example, product life cycles. So one firm I'm talking with is Corning, and they're a supplier of Apple. And Apple has typically yearly cycles, right? So every year they launch a new Apple. They make the glass of the Apple. So they really have this product life cycle, this typical triangle that you see. So this is something that, in DRL, I think using time series that are non-stationary, there's a lot of potential to do research on here. In a lot of problems, we already know the policy structure, but getting the policy parameters is also not that easy. So this is also what I'm doing with these firms, to try to really see, okay, how can we work in environments that are very dynamic. Okay, and the last one really links to what was also talked before with Jan Koen, is a need for human-machine interaction. So one of the things that I also notice a lot when talking to firms is the following. Like, they say, like, we totally understand that we need to build a simulation engine to train the DRL algorithm. Now, the problem often is that if you have a firm and they have a certain policy, that there is always humans that interact somewhere, right? And the previous presentation did a lot of help in explaining what one example is. But in inventory management, that happens a lot. So constructing this simulation engine is not so easy. So in a lot of the literature, we just assume, like, okay, let's sample from the empirical distribution of the demand, etc., and let's just build a simulation model. But how do you really, replicate what humans are really changing in the process? That's very difficult. So one company said, like, okay, we have built like they call it the AlphaGo algorithm for their company. They said we have built the algorithm, but the problem is that we can't really implement it because we don't really have the interaction with humans in this. So a lot of the decisions are sometimes changed by a human, but we don't really know how to model this behavior. And then training the AlphaGo algorithm on company data works very well, but we can never apply it in practice, because in practice there will be humans in the loop. And in that simulation model, which has to train for millions of periods, we don't have the interaction of the human. So what should we do? And I think this is something that also is a very promising next avenue to work on, which I'm currently doing as well. So that being said, am I a bit earlier? Yes. Yes. So that being said, I would like to open the floor for questions. Thank you very much for your attention. Cool.
There he is. Yeah.
Are there questions online? No questions. You answered them all.
Perfect.
All
Thank you
right.
very much.
Thank you, Joren.